Hi everyone, I'm back with another video about heat and mass transfer, and today we're going to be talking about an expression for the overall thermal resistance of a pipe that is surrounded by insulation. So we're going to have a pipe that's going to have some hot fluid running through it, and we're insulating that pipe, so we want to keep as much heat inside as possible. We're going to look at how the thermal resistance occurs with the heat flux going from the inside of the pipe out towards the insulation that is surrounding it. And then from there, we're going to talk about expressions for the first and second derivative of our overall thermal resistance that we get from the first part of the video. So the first thing I'm going to do is write our example here. So I'm just going to draw a picture of our pipe. It's just going to be the cross-sectional picture. Our inner pipe is going to have diameter of R I, and then the outer diameter, radius is going to be R O. So that's just going to show we have our pipe, which is that inner circle, and then the outside is the insulation that's surrounding it, and then around that we're going to have ambient air that's going to be cooler than the inside of our pipe, because on the inside we're going to have that hot fluid in there. So I'm going to go ahead and rewrite our equation that we found in the last video for the thermal change throughout a cross-sectional area of a circle. So that was delta T equals Q times, and then it'll be natural log of the the inner radius divided by the outer radius, or the initial divided by the final radius, depending on which way we're looking at the heat flow occurring. And that's going to be over K 2 pi times the height of what we're looking at. And so in this case, we're going to indicate our pipe length as being the height. So I'm going to go ahead and write that as L for length instead. So this is that equation that we have here, delta T equals Q ln Ri over Ro K 2 pi L. And so that's just what we got from the last. So now that I'm looking at this again, I had it right the first way around. The final radius is going to be on top, and the initial is going to be on bottom. So it's actually going to be natural log of the final radius divided by the initial radius. Alright, so if you recall, this is going to be essentially equivalent to our delta V equals IR from our circuit. So when we're looking at a voltage drop across a resistor due to the current and the resistance of the resistor, that can be essentially equivalated to the delta T, or the change in temperature that we have due to heat flux and the resistance of whatever material we are doing our heat transfer through. So these are essentially equivalent. So our delta T in this case is going to be the same thing as our delta V, and then the heat flux or heat flow is the same as our current flow, and then our resistance in this case is the natural log of the final radius divided by the initial radius over the thermal conductivity times 2 pi times the length of whatever unit we're looking at. And this case is going to be, once again, for conduction. So conduction is going to be occurring when it's between two materials rather than like air or vapor contact. It's going to be like two solids more so. And so this is what we're going to use to evaluate the change in heat flow between the pipe and the insulation that surrounds it. So, since we also have some sort of heat flow due to the influence of the ambient air outside of the insulation, we're also going to have to consider the heat flow due to convection as well, because that insulation is touching the ambient air, and that sort of heat transfer will occur due to convection because it is air instead of like another material. So if you recall, the equation for that was Q equals HA dt. I'm going to write the dt as the delta symbol T. So that's just from Fourier's law. That's our convection equation. That's the heat flux equals the convection coefficient times our cross-sectional area times change in temperature. So we're going to go ahead and rearrange this one as well to be in the same format as the delta V equals IR. So we'll have delta T equals Q 1 over HA. And so our delta T is equal to the delta V, our I is equal to our Q, and our 1 over HA is equal to our resistance. So now that we have both of these equations written in the same format, in that we have the resistance terms defined for both conduction and convection. If you recall from another video, we added these resistances whether they're in series or in parallel. So we're going to do the same thing here to get our total resistance, because that's what we're trying to find is the overall thermal resistance that this pipe is experiencing due to both the insulation around it and the ambient air outside of the insulation. So we're going to add our resistances to get total resistance. And if you notice from this system, this is going to be in series once again, because when our flux is flowing from inside to outside, because we're going from an area of higher temperature or the hot fluid inside of our pipe to areas of lower temperature, which will be our cool air outside the insulation, so that Q is going to be flowing out. You'll notice that in order to get to the air, you're going to have to pass through the insulation and then get to the air. So that means that these resistances are going to be in series because you have to go through both of them in order to get to the final point in your system. You don't get to choose what sort of pathway or whatever, because you're going to have to go through both no matter what to get to the end. So that will be in series. So we can just add these up like normal. So you'll have your natural log of the final. I'm going to go ahead and substitute these subscripts for being what is accurate for our example. So our final R is going to be R naught, or R outer, which is kind of what I was thinking with that sort of dedication. And then the bottom one is going to be Ri, which is our radius on the inner side, divided by the thermal conductivity times 2 pi times the length of our pipe. And then along with that, we're going to add the resistance due to convection. So that will be our 1 over HA term. So this is what I have right now. I just copied over our resistance from the conduction and then resistance from the convection. But we're going to have to change up our convection one a little bit. So we can go ahead and substitute in what our cross-sectional area is going to be due to the convection. Sorry, I just blanked so hard. So we can plug that in for our A term. And then we're also trying to see how this heat flow is occurring throughout the height of our pipe, or as we dedicated it, the length. So we're going to also add our length term in there as well. So I'm just going to rewrite ln R O over Ri k 2 pi L plus 1 over H, and then our our cross-sectional area is going to be 2 pi r naught. So we're looking at the RO, or R outer, R naught, whatever you want to call it, because that's our insulation, which is where our convection is going to occur, is at the circumference of the R naught area. Like that's the interface that we're looking at. So it's that outer circle, that's the circumference of the R naught circle. So this right here, sorry, it's like inverted. That's the interface that we're looking at, so that's why we're plugging that in there, and then once again multiplied by the length of our pipe because we're analyzing throughout that length. So this is going to be our expression for the overall thermal resistance in this situation. Overall resistance. So this is what we were looking for the first part of the video today. So that's awesome. We got this done. So that's our expression right there, overall expression for the thermal resistance. Now we want to look at the expressions for the first and the second derivative of this. And you might be thinking, okay, why are we doing this though? What's the point? So the first and second derivative, if you remember from calculus, can tell you some very important things about your system. So what we're looking at here is the resistance of the heat flow from the hot pipe fluid, the hot pipe, and how that is going to diffuse through our insulation and come in contact with the ambient air. And so what we want to know is how much insulation should we add on the outside of our pipe in order to have the best thermal resistance to maintain the highest heat on the inside of our pipe. So we're trying to keep it as insulated as possible. And if you remember, finding the first derivative will tell you that will set your slope equal to 0. So finding the first derivative is finding your slope. And then if you set that equal to 0, you can solve for where your heat flux is going to be constant. And then from there, you can use your second derivative to find your minimum and maximum values for how thick you want your insulation to be. So if you have a minimum value, then that's not going to be any good because you want to keep as much heat flow from diffusing outward as possible, so you want it to be the maximum term. So actually both the minimum and the maximum will be important to look at because you want to make sure you're somewhere in that middle range to keep as much in as possible and keep as much from going out as possible. So your minimum will be too little insulation amount, and then the max will be too much to where it's not working properly. So it's very important for us to look at both the first and the second derivative. So we're gonna go ahead and derive the first derivative. So I'm gonna denote this as being the derivative of our R total because that's what we solved for before. So dRt over, and then we're going to be looking at this by changing the term the R outer, so R naught, because what we're looking at is how thick we need the insulation to be, so that will vary our radius on the outside being smaller or bigger depending on what the sweet spot is for that insulation. So the R naught denotes how much insulation we have because that's the outside area. So we're going to be looking at the change in the outer radius. So dR naught. So I just have dR total over dR naught. And then now that we're looking at our overall resistance expression, since we're only going to be looking at changes in the R naught term, everything else will be considered a constant. So for that first term with our conduction, we can pull out the k 2 pi l because they're not attached to our r naught term, so those will be considered constants. So I'm going to go ahead and pull those out, 1 over k 2 pi l, and then we'll still have to do the derivative of the natural log r naught over ri. So the derivative of that will be ri over ro. And then you have to do product rule with that. So if you take the derivative of the inside, which is the ro over ri, the ro will go to 1, and you'll just have 1 over ri. And the ri will not disappear because it's considered a constant. So that'll stay. And then for our second part, once again, the h 2 pi and l will be considered constants here because they are not attached to that r naught term, so they can be pulled out front. 1 over h 2 pi l times, and then the derivative of 1 over r naught, or ro, I'm going to interchangeably call it both. That's the equivalent of ro to the negative first power. So if we pull that negative 1 down in front, and then you raise that another power, or sorry, you lower it another power, you're going to have r to the negative second power, so it'll become r squared in the bottom. So that's what we have after the first derivative. So we have those constants out front for both the terms, and then the derivative of our r naught parts there. So we can go ahead and clean this up a little bit. You'll see that the ri's will cancel out in the first term. And then we can also pull out the 2 pi l because that is constant, or that's a common variable in both terms here. Actually, I'm going to leave them with their pieces for now. So I'm going to leave it 1 over k 2 pi l times 1 over ro minus, because we have that minus sign, 1 over h 2 pi l times 1 over ro squared. Oop. So that's kind of our simplified version there. We have, we canceled those ri's out and then pulled the negative to the front of that second term there. And so this is what we have now. So this is going to be what our first derivative comes out to be after we simplify everything. But as I mentioned before, it's also important to see what r naught is equal to when the slope is 0. So when the resistance is not changing, what is our radius at for the resistance to not be changing anymore? So we'll set this derivative equal to 0, and then we're going to solve for, rewrite this. We're going to solve for r naught now. So 1 over k 2 pi l times 1 over ro minus 1 over h 2 pi l times 1 over ro squared. Okay. So we can go ahead and pull off the common term of the 2 pi l, and that will get consumed by our 0. So we'll get 0 equals 1 over k times 1 over ro minus 1 over h times 1 over ro squared. So that's what we have now. We got rid of the common terms, 1 over 2 pi l, and that's what we have now. So now trying to remember how to solve for this. So what we can do, we can pull out one of our RO terms. So if we multiply by RO, everything, then one of it will get consumed in the 0 on the one side, so 0 equals 1 over k minus 1 over h times 1 over RO. So we just multiplied by RO to get rid of the 1 with the k term and then get rid of the squared. And so now we've simplified it down to that. So we can put our k on the other side, 1 over negative 1 over k equals negative 1 over h times 1 over RO. We can just flip this entire equation upside down, and we'll get negative k equals negative h times RO. So our RO is going to end up being k over h. So this value is where the resistance is not changing. So we set that first derivative equal to 0, which means that the slope is not changing, and our slope is showing the changes in our resistance over the changes in our outer radius. So at this outer radius, k over h, or thermal conductivity over the convection coefficient, that's where our resistance is not changing. So this is important for us to keep in mind. Now we're ready to solve for our second derivative. So we have the d squared RT over d R naught squared, and that's going to equal. So we're going to use the more simplified version that we found when we took the first derivative. So we'll just do the derivative of 1 over k times 1 over R naught minus 1 over h times 1 over R naught squared. So once again, our 1 over k remains the same because it is considered a constant due to not having the R naught in there to make it be, derived. And then the derivative of the 1 over R naught is going to be negative 1 over R naught squared, and then we have minus 1 over h, once again the h is constant as well, times the derivative of 1 over R naught squared, so that'll be negative 2 over R naught cubed. So this is what I have here, and now we can go ahead and clean this up a little bit. And I'm going to go ahead and do that first. 1 over k, negative 1 over k times 1 over R naught squared, minus, which will turn into a plus due to the negative 2 multiplied by the negative 1, so plus 2 over h times 1 over R naught cubed. So the only thing I did here was move that negative over, and then move the negative over on the second term as well, and put the h, or the 2 over the h. So now we can go ahead and plug in this value that we found for R naught here in order to only have two components here, two variables. And these are two variables that we actually know the values of because thermal conductivity is related to whatever material we're looking at, and the convection coefficient is also related to whatever material we're looking at. So we actually know both of these values, which allows us to find where the minimum or the maximum, so where the peak is or where the valley is for the thermal resistance. So now we can plug that in. Negative 1 over k times 1 over R naught is now going to be k over h. So k over h squared plus 2 over h times 1 over k over h cubed. So that's what we have right now. Just plugged the k over h's in, and then we can simplify this, multiply the k's by each other in the first term and move the h to the numerator, and then multiply the h's in the second term and move those to the numerator as well. So then we'll have negative h squared over k cubed plus 2, and then that's going to be h times the h cubed, so that'll be 2h squared in the numerator times k cubed again. And you'll see that this works out very nicely in that we can add the numerators together because the denominators match. So our final value will be h squared over k cubed. So now we have this value, and we technically know what these numbers could be if we knew what our material was and we could find the convective coefficient and the thermal conductivity number associated with that material. But we are not looking at a certain material in this example, we're just looking at the theory behind it. So in order to find whether this is our peak or our valley, we have to decipher whether this number would turn out to be negative or positive. So when we're looking at this, h squared, even if the convective coefficient was a negative number, that would still be positive, so our numerator is positive no matter what. The k cubed, that could be positive or negative, because if you have a positive number initially, you'll get a positive number after cubing it. If you have a negative number initially, you'll get a negative number after cubing it. But what we know about thermal conductivity is it's always going to be a positive number. So we know that this is going to be a positive number no matter what values we put into there, because those are both positive over positive. So that means that this is a concave up value. So at the value of the outer radius being k over h, which is where the resistance is not changing, we know that that's going to be concave up, which means that this is going to be a minimum requirement. So if you remember, concave up is right here. So that means that this function that we're looking at, that graph, is going to be concave up, so it's going to be a minimum value. So when the radius is k over h, that will be a minimum value, which means that is the smallest value of the outer radius that we could have without losing our resistance. So now, if we look at this, I drew this graph really quick, so I'm going to draw it again so we can get a better viewpoint of this. So this is going to be what our resistance graph is going to look like right here, and that little dot right there is where R naught equals K over H. That's where we found our concave up to be. So this is showing that our change in resistance, so our resistance is continuing to change until we reach that bottom leveled out point. Our resistance is now not changing. We're at our minimum value, and then we're going to creep back up. And when we creep back up and reach that intersection with the x-axis again, that's going to be called our critical point. So this is where our critical point is the sweet spot for our insulation. So that's when we have passed how the insulation is changing, that is past the minimum value and it's come back up and hit the critical point, which means that that is the best, sorry, my eye just, something in there. So that is the best value that we could have for our outer radius. Because if we do any more than the critical point, then it's going to have an inverse effect of actually making it worse for our thermal resistance. And then anything less than that will be bad for our thermal resistance as well. So we want to hit the sweet spot of being at the intersection for where our thermal resistance is changing. So that's going to be everything for my video today, and I hope you enjoyed.